Good morning.
Morning.
So I'll be going through the notes on mathematical modeling with MATLAB.
Okay.
So I'm going to start the class now. So the instruction is that if you have a question, you can just type it in the chat. Then from time to time, I'll go over the chat and see the questions. Then I would answer it.
Okay, ma'am.
Alright. Let me, before I start, so this class is numerical method with MATLAB.
Okay.
So I'll be using this textbook, Applied Numerical Methods with MATLAB for Engineers and Scientists. So I already uploaded the textbook on Moodle. So most of the lecture notes will come from this textbook. So I decided to use this textbook for this semester. So everything we are going to be doing for this semester will come from the textbook. So let me share. So before I actually start the class, we have before I start the class, I just want to tell you the assessment for this class. So I'm going to be giving you is 70% is exam for the exam, then 30% is continuous assessment. From the 30%, 10% will be assignments and tests and or tests, while 20% is going to be a project that is going to be assigned to each of you. So as we go along in the course, each of you are going to do a project based on the course. And it's going to be 2 people in a group. So the project is going to be 20%, while the assignments and tests is going to be 10%. So all the assignments have been given you on Moodle. It's better you guys take it very seriously because it forms part of your continuous assessment. And let me share my screen for the lecture for today. So I'm going to be talking about mathematical modeling using Visual Basic with Excel and MATLAB. So we're going to start with this model. So this model relates the velocity of a falling object. It gives a model. I think I'm going to mute. So I'm going to mute all of you so that there's not going to be any distraction. So like I said, if you have any question, just type it in the chat. From time to time, I will look at the chat, then I will try to answer it. So we start with the model of a falling object. So this model relates the acceleration of the falling object with the model parameters. We develop the model as V dot is equal to G minus C over M multiplied by V, where G is the acceleration due to gravity, C is a coefficient associated with the air resistance, then M is the mass of the ball, then V is the velocity, then V dot is the acceleration. So we got the model basically from this well-known equation, which is force is equal to ma. So since the force is equal to mass times acceleration, we know that acceleration A is equal to force, the acceleration A is equal to force that's divided by the mass. And since A is the acceleration, we can express A as, we can just express it as V dot. We are going to express A as V dot, where V dot is the differentiation of the velocity. And the forces acting on the falling objects, there are two forces. One is due to gravity, while the other is due to the air resistance. So the one due to gravity is mg, so mass times the acceleration due to gravity, while the one due to air resistance is cv. So this is how we got the model. When you divide both sides by, when you divide this, when you do the arithmetic, we are going to arrive at this model. So this is how we arrived at the simple model of a falling object. In order to solve this, so we need to solve this model analytically. There are two methods that we can use to solve the model. You can solve it analytically. Analytically is you are getting the exact solution for the model. Why numerically? Because this course is numerical methods. So we'll be using numerical methods to solve problems. But because of this model is a very simple model, we can solve it analytically. And when we solve it analytically, equation 2 represents what we are going to get when we solve it analytically. So I'm going to be proving how we arrived at this. In last semester, alpha semester, when we did control theory, we actually did something similar, like we did something similar. So it's just a revision of what we did in control theory. So we start from this. So what we actually want to do is that, given this model, we want to prove that this is the analytical solution. So the first thing we are going to do is that we know that V dot is simply the VDT. That's why we replace this here. Then now we are going to bring this dt to the other side of the equation. So the equation becomes this. Then after that, we integrate both sides together. So I just applied the integral of both sides of the equation together. So when you integrate this portion, you are going to get this. And when you integrate the t, you are simply going to get t plus a constant. So the way we got the integration is that we want to integrate this particular portion with respect to the v. So I can simply put 1 here, then the v here. So the integration of this is going to give us ln of this function we have. Then the coefficient, where the coefficient of v is minus cm. So, and it's 1 divided by minus cm. So that's why we have minus mc. Then after that, we arrive at this equation. Then when you multiply both sides by c divided by m, we are going to arrive at this equation. Then when you you find the exponential of both sides of the equation, you arrive at this equation. Then we're going to make, you're going to cross, you're going to make, you're going to give g to the other side. So this g is going to come to the other side. We have this because our aim is to get v. So we want to let v to be alone. Then after that, we multiply both sides by minus m divided by c. Then we arrive at this. So when we do that, we arrive at this equation. But then G is a constant, and we need to get the value of G. In order to get the value of G, we are going to put in the initial conditions. So the initial condition says that when we started the question, the initial condition is that at V is equal to 0, T is equal to 0. So that means that when the ball starts at rest, the velocity is equal to 0. That means that the ball is initially at rest. So we put in the initial condition in order to get this G, because this G is a constant. So when we put in the initial condition, so at T is equal to 0, V is equal to 0. So we replace T with 0 and we replace V with 0. When we do that, we arrive at this equation. Then when we solve this equation, you would see that the big G is equal to the small g. Therefore, what we need to do is just to plug G into equation 3. This is our equation 3. Equation 3 is here. So we plug, instead of this capital letter G, we plug this small letter g. Then we arrive at this equation, doing some minor rearrangements, then collecting some like terms, we arrive at this. So we've been able to prove that the analytical solution to this model, to the model we started with, so this is the model we started with. We've been able to prove that the analytical solution is given by this. So we already did this. We did this in control, like I said earlier, when we started control theory, we actually did something similar to this. I'm just going over it because I observed that there are other students just coming in and they didn't start with the alpha batch. That's why I decided to just go over it again. So now we're going to, so this is the analytical solution to the model. And when we plug in some constants, we say let M is equal to 68.1, then we plug in some parameters. We arrive at this model, which is the analytical solution to it. Then we try to get the velocity at different time steps. When T is equal to 0, the velocity is 0. You just simply plug in place of T, we simply plug in 0. So when T is equal to 2, we arrive at this. When T is equal to 4, 6, 8, 10, 12. So it's just simple arithmetic. So this is the analytical solution. And when T is equal to infinity, so when T is equal to infinity, when this T is equal to infinity, this exponential will tend to 0. So therefore, the velocity at T is equal to infinity is simply 53.44. That's how we arrive at V infinity is equal to 53.44. And the solution I just explained now is called the analytical or exact solution. And this model is a very, very simple model, is a simplified model. And that was the reason why we were able to get the analytical solution for it. And remember, this is the analytical solution we derived when we proved it from the model. And it's because it's a simple model. That's why we were able to get the analytical or exact solution. There are some models that are very, very complicated. And no matter the amount of maths you know, you might not be able to solve it. It is impossible to solve it analytically because the analytical solution is the exact solution. And some models are very, very complicated. You would see as we go along in this class. And like I said, it might not be possible to solve it analytically. So that's where the numerical solution comes in. And remember the title of the course is Numerical Methods Using MATLAB. Essentially, what this course is about is trying to solve models, trying to solve engineering models using analytical solution. We can go through using numerical solution. We can decide to use the analytical solution, but there are some models that is not possible, or solving the analytical solution is very tedious and very time consuming. So we have to go through the numerical solution. Then how do we solve it numerically? We use the Euler's method to solve a model numerically. So I actually gave some assignments, and when I went through, for those people that have submitted, they actually used the Euler's method. So um, I know that you guys know how to use the Euler's method to solve mathematical problem. So what's the Euler's method? The Euler's method makes use of the first two terms of Taylor's expansion. We also did this last semester in control. So when we did control theory in the last semester, I told you that in order to relate, this is a differential equation V dot, and this is in time steps. Like this is when you want to represent it on your computer, when you want to use time steps K. This is the equation. Then I told you that actually Taylor series expansion is an infinite series. And the actual Taylor series expansion for the next state is given by, I'll just try to write it there. It's given by delta t squared, then 2 factorial, then v sub k, double dot. Then the next coefficient is the third derivative. So you have delta t raised to the power of 3, then 3 factorial, then v triple dot. So here you have v triple dot. It is v triple dot. But for the Euler's method, we are just going to make use of the first two terms to approximate the model, or to solve the model numerically. So for Euler's method, we are making use of the Taylor series, but you are just making use of the first two terms. And now our model, this is the model we were given, and we want to solve it numerically. We are simply going to plug in the parameters into the model. So when you plug in these parameters into the model, we're going to arrive at this. Then when we need to apply the Euler's method, then we are going to make the time step, the delta t, to be equal to 2 for the purpose of this class. And when we place in, so this is the Euler's method, in place of v dots, we are going to replace it with this, which is the model. So in place of v dots, you have this. Then when you do the arithmetic, you are going to arrive at this model. So given this, the model of the falling ball, this is the numerical solution we are going to arrive at. Then we start from when k is equal to 0. So when k is equal to 0, you have v1 is equal to this equation, and it's going to give you 19.62. So you can keep iterating when k is equal to 0, k is equal to 1, k is equal to 2, 3, 4, 5. Then you're going to get all these values. When we compare, remember this is the numeric solution. The numeric solution is just an approximation to the exact or analytical solution. It's not the exact solution. So like I said previously, the analytical solution is the exact solution and is the most preferred solution. But unfortunately, most engineering problems or engineering models, you cannot solve it using the exact solution. So we have to go for the numerical solution. When you compare these values, this is the values we got for the numerical solution. If we compare it to the exact solution, so this is the exact solution, you can see that there are some errors, there are some differences, but generally it's almost the same thing with the analytical solution. And in order to get the steady state velocity, so we did this in control also, you just make the solution, the model to be equal to 0. So that means that at t is equal to infinity, this is the velocity. So like I said, the Euler's method, we are going to be using the Euler's method. The Euler's method uses the first two terms of Taylor series expansion. But in order to be much more precise, you can decide to use the first three terms of the Taylor series expansion. So here, I tried using the first three terms of the Taylor series expansion. Then I got these values. Are these values are kind of more closer to the original solution, though it's not still the same as the exact solution, because we are just trying to approximate. And when we plot the graph, this blue curve is the curve for the exact or analytical solution, while the red curve is the curve for the numerical solution. So we can see that some difference exists between the analytical solution and the numerical solution. The reason why there is a difference is because of the step size, meaning that the step size is given by delta t. Delta t is equal to 2. That's what we're using when we try to solve for the numerical solution. If we had said that delta t is equal to 0.5, we're going to see that it's going to be much more similar. The exact and analytical solution would converge, and they will be almost the same thing. And now we have been able to solve engineering models using the AND method, but then we want to be able to use a computer. We don't just want to use manual calculation, because if we're to use manual calculation to solve the model numerically, so numerical solution, apart from the advantage, remember I said that the numerical solution, it helps us to approximate the analytical solution. And some models you cannot even get the exact solution. So sometimes you don't even have to bother yourself with the analytical solution, because getting the analytical solution is tedious. So we have to opt for the numerical solution. So we know that it's better for us to use the numerical solution. But then we don't want to, in this course, we don't want to do the calculation by hand. We want to make use of a computer to help us to do the numerical, the solution for the numerical, solving the model numerically. We want to use a computer to help us to do that, because when we use the computer, we can take the time step to be much more smaller. We can take the time step to be 0.1, and when we take this time step to be smaller, then we get smaller errors, and the numerical solution approximates better with the analytical solution. So we are going to be using a computer, and we are going to be using MATLAB and Visual Basic Programming to do this. So I'm going to be illustrating how to solve this model. The model that we solved, we did it by hand uh, previously. Now we want to use a computer to help us to do it. So when I finish the example, you're going to understand. Okay, somebody has a question. Can you type your question? Can you type your question in the chat so that I will just look at it, then I will answer it. So if you have a question, just type it in the chat. I'm going to go look at the chat from time to time. Then I'll look at the chat from time to time, then I'll answer the question. So now I want to use Excel to actually solve this problem. This problem we just did. We did hand calculation, but now I'm going to use Excel first, Excel Visual Basic. Then after that, I'm going to use MATLAB to solve the problem. So I'm sharing my MATLAB screen now. I'm sharing my MATLAB screen now. So I'll just label the name of the problem as the falling ball. So we want to be able to get the acceleration of the falling ball. Okay. So Omolola is asking for step sizes. If we use smaller size, won't it make the problem impractical? Or are there some applications it will work well with? Okay, thank you for the question. If we use smaller step sizes, okay, let me go back to the notes. If we use smaller step sizes, it's not going to make the solution impractical. It's just like now, for this problem now, I said let the step size to be equal to 2. If I have said that let the step size to be equal to 0.5 or 0.1, so instead of this 2, you have 0.5, then you have a new model. So that means that it's using a smaller step size is going to make the solution to be much more accurate, because here we used a step size of 2. Then we discovered that this is the analytical solution in blue, and this is the numerical solution in red. There is a large difference between there's a large error between the analytical solution and the numerical solution. But when we use a smaller step size, we can use a smaller step size, but if you are doing the hand calculation, using a smaller step size will make the problem much more tedious. For instance, now, if I had used a smaller step size of 0.5 here, if I had used 0.5, in order to get to 10, I have to do 0.5. So let me just write it. I have to do V 0.5 because I'm using a step size of 0.5. Then the next one is going to be the velocity when t is equal to 1. Then 1.5. Then I need to get the solution of all this. So before I get to 10, remember I stopped at 12. So before I get to 12, it's going to take lots more calculation. So using a smaller step size is actually very, very good. But when you are doing the calculation by hand, the calculation becomes much tedious by hand. So that's why we need to use a computer to do the numerical solution for us. And when we use the computer, we can use a smaller step size because the computer is going to do it for us. So we are not worried about doing lots of calculations. So I hope I answered your question. So let me go back to the Excel sheet. Okay. So we want to solve the problem using numerical solution now. And like I said, numerical solution is better in the sense that it's the computer that is going to use it, that is going to do the calculation for us. So now I need to specify the parameters. So let me specify the mass of the ball. So I'll say M is the mass of the ball. So I'll just use the same parameters I used when I was doing the calculation by hand. So let's say the mass is 68.1 kg. Then the coefficient of air resistance, we specified it as 12.5 kg. Then the step size, is 0. Let me specify the step size as 0.1 because now we're using a computer, so it will be much more faster. Then we need to, let me say G, that's the acceleration due to gravity, is 9.81, is a constant, ms squared. Then we need to, so the time, let's say the time step is 0, 2, 4, 6, 8, 10, 12, 14, 16, 18. Let me stop at 20. Then let me indicate the numerical solution here. So this is the numerical solution of the velocity ms squared. Let me use this box to indicate the analytical solution. So V analytical. So the unit is m squared. So now I have these parameter values now. Then I want to solve it using both numerical solution and analytical solution. So the first thing I'm going to do is to assign label names to these values. So this is the way we do it in Excel. You select the label together with the values. Then you go to formulas. Then you click on create from selection. The left column will be automatically selected. You click OK. So now this name M has been assigned to this value 68.1. When I click this value 68.1, you can see M showing here. So that is showing that the value of M, the value of 68.1 has been assigned to M. The same thing, when I click this one, 12.5, you have CD. So that means that this value has been assigned to this. Same with this and same with this. So 9.81 has been assigned to J. Then when we do that, we do the analytical solution. So in order to verify the analytical solution for this, when T is equal to 0, okay, you have a question. You can go on and type your question. Opeyemi, you can go on and type your question. Okay, so now I'll just go on. So you click on this box because I want to get the analytical solution at, I'm lost from the part where you were going to insert formula. Okay, all right. I'll go over it again. But I have, because I'm using the basic version of Zoom, and I only have 40 minutes. So what happens is that when this time expires, I'm going to end the meeting, then all of you will rejoin using that same link. So I hope you all understand that. So what I'm saying is that this time, because I'm using the basic version of Zoom, I only have 40 minutes and I have less than 5 minutes to go. So I'm going to end the meeting before the 5 minutes expires. Then after that, you guys are going to rejoin using that same link. Using that same link. Okay. Thank you. You said you understand that. Okay, for Okoyemi that said I I went over it very quickly. So let me go over it again. So I typed in I typed in these values. I specified the mass as 68.1, which was the same thing in the question. The coefficient of air resistance, the air resistance coefficient, I specified it as this. Then the step size, I specified it as 0.1. Then the acceleration due to gravity, I specified it as this. Then now I need to assign variable names to all these values. I need to assign variable names to all these values. So to do that in Excel, you would select the name together with the values. You will select the name together with the values. Then after doing that, you will go to the formulas tab. You go to the formulas tab. Can you all see me? See that I'm selecting the formulas tab because I want to be sure you can see my screen. Okay, thank you. You go to the formulas tab. Okay, thank you. You go to the formulas tab. Then when you go to the formulas tab, you select create from selection. Create from selection. Then when you select create from selection, this left column will be automatically selected. So what this is saying is that assign this variable name to this value. Assign this variable name on the left to this value. Assign this variable name on the left to this value. Then assign this variable name G on the left to this value. Then you click OK. That's what I did. Then once you do that, when you click on a value, you can see on this box the value shows, then M shows. So that means that this variable name has been assigned to this value. So when I click on this variable name has been assigned to this value. Same with this, same with this, same with this. That's what I did. Then in order to do the analytical solution, I want to do the analytical solution when t is equal to 0. So I click on this box here, then I type in this formula. So this formula is simply the analytical solution. So if you go back to the notes, we got the analytical solution as m times g divided by c multiplied by 1 minus exponential c divided by m times t. So this is the way in which we are going to represent it in Excel, because you guys, I'm very sure that you guys know how to use MATLAB. So is the same syntax with MATLAB. So instead of that equation for the analytical solution, you convert it into this form in order to be able to use it in Excel. Then in place of this, here is supposed to be t, but we are saying that let t be equal to 0. So we say A9. So this box here is for the value of t. So I used A9 instead of t because here we have 0. So I just said when t is equal to 0. So that's why I did it this way. Then when you click enter, you're going to get 0. Then Excel is so good. So if I want to do for this second, for when t is equal to 2, I change it to 10 because at A10 you have 2. So when I click enter, you have the value. So in Excel, I don't need to keep on typing the formula. I just need to drag it from the right hand side. Then here, So yeah, I've gotten the analytical solution. I've gotten the analytical solution. So when you click on this is the formula. So this is the formula for the analytical solution, but this is how to represent it in Excel. So I have less than 1 minute now. So I'll be ending the meeting now. Then immediately I'll be rejoining using that same link. So I'm expecting all of you to rejoin using that same link. So I'm ending the meeting now. Then all of you should rejoin using that same link in on Moodle. All right.